Hey, welcome back. We're working on project 4. I'm just checking our stream and making sure we've got video and sound, so it seems like things are going well. Cool. Thanks so much for the work on project number 4. I saw a lot of great work. And then also like some people trying to figure out like where these different resources were. There are some links like in this description. It's not meant to like hide anything from you. It's meant to like just have ways to approach this so that you can post-process the material. So general kind of finite element process is that there's a pre-processing step. That's where you define the node, like what elements you're using. So in this case, we're using like 2 elements that have 2 nodes, so they can only stretch or compress, and that's it. Like there's no bending stiffness to them or anything. And then the geometry, so like where they're all placed, all of that is kind of taking, all that pre-processing is taken care of in this extra FEA material in this notebook here. So some background on how this stuff is set up. The main thing that we're doing here is solving the problem. So once you set up where everything is, what the problem looks like, how you're meshing this structure, then you can say, all right, all of these elements are steel or aluminum or whatever material you want to use. In this case, all we need is the Young's modulus. In general, we would need modulus and Poisson ratio, but here we're only stretching, so we don't care about how much the cross-sectional area changes as we stretch or compress. That would be the Poisson ratio. And then once you've done that, it turns it into one big linear algebra problem where we have a stiffness matrix K, displacement vector U, and applied forces F. So one way to approach this is that we apply forces everywhere on this whole matrix. So we say that we know what all the external forces are, and then we solve for U. But what we found in that first homework is that if we try to do that, oh, I guess it's down here, huh? np.linalg.solve of K, or not solve, what am I doing? COND, we want the condition of K, like this. We end up with a very high condition number for that stiffness matrix. Because if you remember from homework 4, we have a very similar problem where it's only one-dimensional instead of two-dimensional. Here, what I could do is say that I know force on the left side, I know force on the right, and let me apply things that way. But we couldn't solve this problem. And the same thing would happen if we try to do that here. So instead, by saying that we're just using that inner 2 through 13 stiffness matrix, and here np.linalg.cond of K 2 through 13, 2 through 13. Now we have a condition number of 52. And you can also look at like the determinant. So trying to invert this thing, usually we never want to invert a matrix, but the determinant is 0 in this case. This one, determinant is 0. I haven't done this before. Now that I'm like doing it on the fly. Why is that so close? They're both like different powers of 0. I'll have to think about that. Maybe EA times K. Yeah, so here determinant is 10 to the 20, and here it's 10 to the negative 22. So when I try to divide by this, I basically get infinity, and over here I'm dividing by a large number. But anyway, condition number is a better way of trying to figure out what the approximate error is going to be. So in the first case, if my condition number is 10 to the 16, then the error that I would expect, print so it's going to be 16 minus 16. Best case for doing problems with floating point numbers, it's kind of 10 to the negative 16. So this is my value of c. So 10 to the c minus t is telling me that my expected error is around 1 on all these things. And then down here, I can say print, well, let's just do this, copy this, paste it down. I'm going to call 52 a 1 minus 16, and now I get 1e negative 15. And really we're doing like yeah, it doesn't really change it much, right? Like even multiplying by 200. So I wanted to see what the difference is with and without that e times a. And for the most part, we're still talking about ten to the 16 kind of condition number. Cool. So that's like this first part, is identifying like why are we splitting this up? Like why are we solving this problem this way? Like just that one. And what this is doing is the way these displacements and forces are organized. We have 7 nodes, which means there are 14. So each node can move in x and y. So there are 14 displacements that we need to solve for, and 14 forces that are either applied or we're going to solve for. And there's a mix and match, right? Like some of the nodes, we already know what they're doing. So node 1, x and y, which is 0 and 1, we know both of those are 0. Node 7, y, we know that one's 0 because it's not going to move up and down. So it's on a roller position there. Yep, and that's what this one is saying. Cool. So now I can jump into like actually trying to solve this problem. So I did a little bit of background thinking about like why am I setting this up this way, and how am I going to solve this. So what I can do now is I'll say say that this is steel, E is 200, E3, and I'm using megapascal, which is a Newton per millimeter squared. So my area is 0.1 millimeter squared. F is going to be zeros of 11, but then F5 is negative 100. Is that right? Negative 300. Sorry about that. So 300 newtons applied directly at the center right there. Then let's do this. I want to add another cell up above from scipy.linalg import LU. LU P, L, and actually I'm going to use capital letters here. And I'll do this LU decomposition. I can see here that because my stiffness matrix, I don't really need to pivot it at all. So this pivot matrix is just the identity matrix. So whether I want to use it or not, the transpose is the same thing. True, 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 true. Like there's nothing. So I am calculating a pivot matrix with that LU, but I don't really need to use it. In general, I might have to, but if I'm checking it, so I could make a note to myself, P is identity matrix. And then L should be a lower triangular matrix. U is this upper triangular matrix. So what I'm going to do first is solve for just the nodes that can move. So node 2, xy, 3, xy, 4, xy, 5, xy, 6, xy, and 7x. So all those 11 displacements. That's what I'm trying to solve for. I'm going to call it U free. And this is going to be linal.solve of U comma y, but in order to get there, I need a y equals linalg.solve of L comma F. And I need to divide by E and divide by A, because, or multiply EA times L or U or something, like somehow that EA has to be there. I think the easiest way is to put it in the right hand side since I can divide it through. And then I'm gonna check out all the free nodes. Where did they go? So the biggest displacement that I have, so here this is node 2x, node 2y. So it moved to the right and down. Node 3 moved to the right and down. Node 4 moved to the right and also down. 5 to the right and down. 6 to the right and down. And then 7 just to the right. And then there's another 0 that's not there. Cool. And as far as solving it, that like I solved one part of the problem. I know all the displacements of this truss. So the next step is solving for what are the forces that were applied, what are all the reaction forces on this structure. And this might seem easy at first because I just have this 300 down, so there's got to be overall 300 between the two. But it would also solve like a sum of the moments problem here. So I want to say, and here, let's call this FA for F applied. Oops, and I hit insert on accident over E. And that didn't change anything. So now F, the total forces that are applied is E times A times my full K matrix. I'm going to use this at symbol. At, get it back, times U. But U is not just U free. Well, I can try it and show you what happens. It tells me like, hey, you're trying to multiply 11 times 14. So what I need to do is say U is zeros 14. U of 2 through 13 is U free. And now I can say times U and look at F. Some things that I'm checking for when I'm looking at this is there are no applied X forces. So this reaction force on node 1 in the X direction should be 0. It's 10 to the negative 14, which to me is basically 0. So that one's fine. Same thing here at node 7. There's no forces applied there because that one is on a roller, so the roller's not applying anything. Here's my negative 300 force down on that node 4y. And then here at node 1 in the y direction, I have 150. Node 7 y direction, I have 150. So 150 plus 150 all equals 0. Nice. And that's what should happen, because if I take f of 0 colon colon 2, these are all the x direction forces, np dot sum of those, they all add up to 0. And then if I start at start at 1 and go to the end and skip every other one. So that's what that colon colon 2 is. So start at 1, take steps of 2, and the missing value means go to the end. So 150, 0, 0, 0, 0, 150, and then negative 300. All of the applied forces add up to 0. In the x direction and the y direction. And that's what it should be, because this thing is not going anywhere. So I have displacements, I have forces. Now, really, I've solved the problem. Like, I have all the solutions. The next step is trying to post-process this and kind of like visualize. So that's the last step of finite elements, is like post-processing. Meshing, sometimes you want to see like what stresses there are, what the applied forces are, and all of that. So if you look at the FEA material, the last thing on here is this function kind of built to post-process FEA results, and it's specifically for this FEA problem. Here, if I just do like a kernel restart run all, it'll run all those, and then the last thing that I get is like this scalable deformation of the same structure, same boundary conditions, same applied forces. But even if it was different applied forces or different boundary conditions, it would plot this structure the same way. So I can grab this. I don't even need this interaction thing if I don't care about animating it. And let's look at a scale of 5. So S is that scale, and it's going to tell me like, hey, R is not defined, and also this IX and IY are not defined. So I'll jump back in here, do the same thing. Like, all right, well then where is R defined? Coming back up here. Same thing that at least that we've done in the past, of like, go back, figure out where are these definitions? How do I edit some code to make it work for me? Nope, not that. So paste that in there. Now I have IX and R and IY in there. So let's see how that one works. Now it's telling me that nodes is not defined. And nodes, I saw some people trying to like build the nodes based on, I think, like where you thought these nodes might be, which was probably kind of hard to figure out based on this. I mean, they are in there, but I saved the nodes inside this FEA arrays, so I can say nodes equals FEA arrays of nodes. And now I have an array where it lists, so each node is given a number, 1 through 7, and a location, X, Y, X, Y, X, Y. So now I have nodes defined, I have R, I have U, all of that. L is not defined. All right, that's annoying. So, and then L equals 300 millimeters. There. So now I've got my post-processed results from that extra FEA material. So some missing things were like getting that function copied over and then using that IX, IY, and R. This is just the reason that I built it this way was so that every truss is drawn as a triangle. Because if all you do is grab the X locations, and it's going to draw kind of a zigzag, like a Charlie Brown zigzag shape, and it's not going to show these like cross structures. Because really all we're doing, the only thing we're keeping track of in this finite element simulation is where are these nodes moving. So I just created this like post-processing function to draw triangles between all those neighboring points. There's other ways to do it, but this is one of the ways to do it. If you're using ChatGPT to try to help you with this, I don't know, maybe you could upload this extra FEA material into ChatGPT and say like, hey, this is what I'm working with. Can you help me figure out how to post-process? So those are the words that you need are like post-process, visualize, plot, like that kind of stuff. Okay, I've got steel covered. So this is the displacement and deformation scale. Let's do this too. I'm just creating steel deformation scale 5x. Cool. Now let's repeat this for aluminum. And what should we do? Just copy these two. Copy. So I'm highlighting the two things, hitting C, or you can hit edit copy cells, and then come down here. You gotta hit V for paste or edit paste cells. For aluminum, main thing is that now we're down to 70 megapascals, so this is a lot less stiff. Same cross-sectional area. Already, I reduced the stiffness by more than a factor of 2. I'm expecting these values to go up by more than a factor of 2, and let's see what happens. My Y displacement is now almost 50 millimeters rather than 20 millimeters, so more than doubled. The forces did not change, and I don't know if you expected that or not. I did expect it, because if I apply 300 down, there's got to be 300 up, and whatever material there is in here, it does not matter. Like aluminum, steel, plastic, cork. The only thing that can happen is that it breaks, but that's a different problem. This linear finite element is not going to tell us, did it break? It's just going to tell us, based on this stiffness, where did things end up? Okay, so now I've got all this kind of recalculated. So let's run this. I don't even need to rerun that function, right? All I need to say is material equals aluminums, and boom, a lot bigger displacements. Everything moved a lot further, probably to the point of fracture for these tiny little 0.1 millimeter squared bars. So probably, and really, like if we look at a scale of 1 for both of these, then it's not quite as crazy. I mean, here steel, it looks like it's not moving at all, but that's just because it's 300 millimeter long bars that are deflecting by 12 millimeters. And down here we see a little bit more. So here that deformation of 1x might be a little better, might be a little bit better than like our 5x deformation scale. Okay, cool. We've got a model. We think it's working. We haven't done like a verification step, but we have like 2 different materials to see as we change the material, how much is that deflection changing. Now let's use that model to do some engineering. So the question here is, how do I keep deflections less than 0.2 millimeters? There's more than one way to do this. We learned in module 3 about root finding methods. So I could define a function that returns 0.2 minus this biggest deflection. So like that 0.2 minus 46. Right now the error is 45.8 millimeters. So pretty large error to start. Or I could use the fact that this is a linear algebra problem. If the area increases by 10, all the deflections decrease by 10. And if we're not really sure about that, let's try it out. Double the area. Right now my biggest deflection is 46. I doubled it. Now my biggest deflection is 23. Exactly 1/2, because it's a linear algebra problem. So no matter how complicated finite elements get, if I'm using linear algebra, if I'm setting it up as a linear algebra problem, it's still a linear problem. So I could use that to my advantage. So I can grab, what do I want to do? I want to calculate like, here, let's do this. U max AL equals U free bracket 5, like that. 0, 1, 2, 3, 4, 5. And that's the same place where I applied the force. So it makes sense that that's the max displacement. And let's do the same thing up here. U max steel is U free of 5, and I'll rerun these. And let's keep it in order. So steel was 16, aluminum 46. So if I want the new area to be, the new area to make this number go to 0.2, then what I want to do is say that 0.2, or sorry, 0.1, area over 0.1 equals divide by 0.2 times 16.12 times that U max steel. I think I'm doing this right, but we'll find out in a second. So this is telling me, oh, well, it's negative because that U max is negative. So let's make sure our area is positive. So 8.06 millimeters squared is what based on just a linear analysis of saying like, I want the deflection to be 0.2. My original area was 0.1. So let me take the ratio and get it to the right value. And this should work, but the real way to check it is actually run the analysis again. So come back up here and just grab these steps. So let's print steel area. We'll comment that one out and do AST like that. So we're saying steel area is 8.06, and when I look at all these deflections, sure enough, the biggest one right at node 4 Y displacement is exactly 0.2, which is what I wanted. And what did I do? Oh, let's put the so many typos, right? Steel area. Oh, whoops. U max steel. What did I do wrong? It's working now, but it keeps flip-flopping back and forth. So I'm trying to see what I'm doing wrong. Oh, this one. I don't need to calculate that again. All right, so let me rerun the first one, because what's happening is I'm recalculating the max displacement and then undoing the optimization that I just did. Okay, so now every time I run this, I'll get the same result because I'm not recalculating. So I get that negative 0.2. Deflection, so steel area 8.06. Cool. Let's just, well, we'll copy paste, right? We'll say 70, not 700, 70 E3. And now we're going to use AL. Aluminum area, AL, AL, and now I want to delete this, call it aluminum, and let's see what we can do there. And I guess I don't need this anymore. That was just some bookkeeping. My area for aluminum is 23.04, and sure enough, the largest deflection that I get is 0.2, which is exactly what I want. And whether or not you want to deal with a factor of safety is a different issue, but here, if this is the goal of like, what is the minimum cross section for 0.2, then I've gotten there. I can show like, all right, if I have anything bigger than this value, this number will go down. And same thing here. Anything bigger than this, that number is going to go down for aluminum. Now the last step is I just need the print total weight. I like to do it in kilograms personally. So I have 0.3 meters times the AL, This one, I want to say times 1e -3, so -6. So to get millimeters squared into meters squared, yeah. So 0.3 meters long times that. We have 11 beams, so there are 11 times 0. Let's put that over here. 11 times 0.3. And then the last step, so now I've got a total volume. Last step is times that 2,700 kilogram per meter cubed to give me a total kilogram. So here it's 0.2 kilograms. Colon 1.2 F. Like that, 0.21 kilograms. And let's just copy this up and paste it in here. Now I just need some steel in there. Steel is not 2,700, it's more like 7,900. And a steel, cool. And we get total weight 0.21, 0.21. What? If we do like 3 sig figs, we'll see a little bit of a difference. Let's make sure, like they should be a little, there we go. So by using aluminum, we use more material, but we do save 95 grams. I don't know, could be good, depends on who you're talking to. But aluminum's a little more expensive per kilogram. But anyway, yeah, this is how we can take finite element model. And again, like the main solutions here are like these two outputs, just like this collection of numbers. That solves the finite element problem. Everything to like get it into this plot, that's all like post-processing stuff to make it look, to visualize it and see what does it look like when we look at the structure in the final step. So, anyway, hopefully you've enjoyed these projects and these modules. If you're working on module 5, cool, like jump into something new. Other option is go back and revise this modules 1 through 4. Either way, you can get those points back and finish out the course. Everything has to be turned in by Sunday, and because on Monday morning I'm going to submit grade. So whatever I have, that's what I'll grade on Sunday. And if things are coming in later than that, or something's not working for you, then you got to reach out to me. I won't answer emails over the weekend, but on Monday, kind of reach out and maybe set up a meeting or something. Okay, all right, thanks a lot. Keep up the good work. I mean, well, the work is mostly done at this point, but keep it up. We're basically done after you turned in this. So everything from here is just kind of getting your grade to the place that you want it to be. All right, thanks. Have a great weekend, and thanks for joining.